to demonstrate two things. First of all, we perform impedance measurement in time, what's, let's say, rather untypical for, let's say, for classical devices, as a first thing. And second thing is combination between electrochemical effect and the optical effect. And like I say, in some cases, the difference between, let's say, imprinted water and not imprinted water is extremely low. And for this case, you have to amplify basically all this phenomena. And this is pure water. So what I'm doing, I will fill both containers with pure water. Okay, done. Just a comment, the whole electrochemistry is sensitive. It's not super sensitive to temperature, but it's sensitive to temperature. And also it's sensitive to, for instance, when I touch it with my hands, then, I mean, it's well visible basically in the measurement. So just, I mean, handling it requires a little bit, let's say, understanding that during measurement you can basically change your samples. Okay. Then here I, let's say, this is a phytosensor, close it, down, down, down. Okay, I connect it to this device now. And what I will do, we will perform measurement in time at a fixed frequency of 450 hertz. So it's basically a device is sampling, 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 and I mean, you will see. I put it here that you basically see what is happening there. Okay, here you see these two cards. This is channel one, red one is a red one, black one is a black one. Well, and now I would like, let's say, to excite fluid and to see a dynamical response from a fluid. So for this, we implemented this excitation mode. It has high frequency and low frequency. You can understand as a modulation with two frequencies. So as the first modulation is about up to 12 megahertz. I think it's now 1.1 megahertz. And low frequency modulation is about 0.5 hertz. So, and now it starts this excitation. We will see this basically as a change of dynamics. So this impedance dynamics. And what we will do now, we switch to, like I show in my talk, we switch to statistics. And now the system is calculating other statistics. Okay, what are parameters of the noise? What we have? No, it's basically, I mean, it's not really. We don't need to run it a long time. Well, so it's basically 2-3 minutes. It's enough, at least for this demo experiments. Okay. Well, where is my client? I think this is enough. We see about, I don't know, 20% roughly. Yeah? And we can, of course, put more characterization. We can, for instance, go in more details. What are, for instance, what are specific peaks? We can explore dynamical aspects. We can change frequency. We can, you see now we have multiple parameters. We go through the scanning frequency of impedance spectroscopy and go through spectra. We excite now with blue light with 470 nanometers and with a frequency. So we have 1.1 megahertz and 0.5 hertz excitation. Okay. Well, now we stop it. And what I will do, I will stop excitation. What I will do, I will now just replace one of the channels, just from this double differential approach. So we're measuring control to control, and now we're measuring control to experimental. So we, in this case, we perform a kind of relative measurements. So. At the moment, moment is channel 2 is untreated, is a control, and channel 1 now I change, also I replace by treated water. By chemically, let's say postpone this question after this. I mean, let's see what. Yeah. Okay, what I do now, I start new file, new measurement, and first I start the measurement again. This is more or less what we had in the impedance scope. And now I start the same excitation with the same parameters. And I switch to statistics. So, and we immediately see more or less response, dynamical ionic response of fluid is almost 10 times different. So it's the whole measurement took about, I don't know, 2 minutes. Yeah. Of course, it should be performed with more controlled condition, light, temperature, and so on and so on. And I think it's basically it's enough. So the major point here that what we can demonstrate as a first, okay, we switch off excitation, we switch off measurement. Okay. The main point, what mostly people ask, okay, is the difference between my chemically equal fluid, because fluids is chemically equal. I mean, that's the point. Here, of course, we have some issue with temperature, because temperature probably not absolutely the same. But temperature, like I said, is head impact, but at least not so huge. There's not really dramatic impact. Well, okay, now the question to the technology. Frederick, could you say something about this technology? Yeah, say little bit, I mean.
Hi. I'm the provider of the informed water. And in fact, I'm a practitioner for the last 20 years. And for the last 3-4 years, I've got a biotech. And where we've been trying to bridge the gap between the domain of coherence and biology. And very simply, we created a range of products which are informed water, which have got very particular actions in biology. And we have different proofs on inhibiting Borrelia, H. pylori, Campylobacter bacteria, and some proofs on physiology, on replication of cells, on inflammation, on decreasing inflammation. So we've got lots of different products with different actions to work on the biology. And the way we inform the water, obviously, is a bit of a trade secret. But it's the domain that the gentleman is going to talk about tomorrow, which is all about frequencies and digital informations. Exactly, as well.
Okay, thank you. Well, this more or less cases what we quite frequently have, some, let's say, practical request, concrete technology, and, more or less some clear result what we see finally. Okay. Any question to this part? Because here, you see, it's a little bit different usage. When in the first case, we just run more or less in the classical way, by using frequency analysis. In this case, we consider the whole system as a non-stationary system and say, well, impedance changing at time. Impedance is, let's say, the dynamic response what we're measuring. We can measure with statistical methods and, okay. Yeah.
I'm sorry, I didn't understand. You said that you excited with 2 different frequencies.
Yes, yes.
I didn't understand what, do you excite one vessel with one frequency, another with another, or?
No. Both, yes, both. It's important. The reason why we basically do this differentially because both containers are at the same light, at the same condition. I'm in here, impact both in the same way. So excitation is also the same. Of course, it should be the same. So what I mean with this double, let's say, two different frequencies, you can see kind of, let's say, high frequency modulation. So we excite it with, let's say, 12 megahertz or 10 megahertz, and then we switch off, switch on this modulation with a sub-frequency, sub-frequency, something like 0.5 hertz. So it's a kind of double meander modulation. This is more or less experience from our generators. We use generators, and they work exactly in the same way. And then we say, well, it could be a good idea to use them for, like I said, the whole story now, and that was my question to near-infrared spectroscopy. I mean, a combination between electrochemistry and optical phenomena are not fully understood. And what we are starting now, we're starting to explore this. I mean, more, let's say, practical way, but we have now devices and we can explore this. Okay.
You say you used information that you imprinted right now. You used it to imprint, like IC medicals. Is that what we're talking about? Something like that? Or just frequencies? But the frequency, let's say, is for bacteria X, and then you used another frequency for bacteria Y? Or you used exactly the same frequency right now in this experiment? Different frequencies, and you can determine the difference with your system. Just trying to clarify it in 2 words. Yeah.
Well, at least from our side, we try to be decoupled from, let's say, imprinting side. We say we don't know. It's a black box for us. It's more or less, as a kind of control, as a test for us to receive, for instance, equally imprinted or not equally. I mean, we are testing in this way ourselves. So we don't know what's happening with fluid, and basically we are not interested in this. For us, is to see whether there is a difference between control fluid and experimental fluid, and that is all what we said. That's the first point. The second point is to characterize. For instance, the simplest what we think now, we perform already some experiments to define, let's say, 5, 6 groups of impact, or this experimental, let's say, technologies, where we can classify, okay, these things like group 1 or group 2 or group 3, and put a little bit more. It's more or less what with near-infrared spectroscopy, but let's say more from the viewpoint of dynamical ionic response. So that we know, okay, there's a reason for this, we know classes of this impact, and can, let's say, provide more information. Okay.
Well, I saw that you speak a frequency of 550 Hertz, and the second one, which I didn't catch because you are too quick, 1.1 megahertz. But I don't really understand what. How do you use the 2 frequencies?
Can I use it? Yes. It's more or less in the way, but like I said, it's just our implementation. You will see here the 1 megahertz.
Yeah.
And again 1 megahertz.
Okay, thank you.
It's a kind of combination of low frequency.
Okay, thank you very much.
Sorry.
I have a practical question because I work with devices, time waver devices from Germany, which are able to, as a practitioner, but I inform water as well. On the one side, like information on quantum level, and on the other side, I work with a second device with frequencies, and I can also treat water with frequencies. And now you said, if I understood you well, that you treated the water, the second parts of the water with frequencies. And it... okay, I name it not properly in English, but you put frequencies to water, but the other part of the water, the second one, you said it was imprinted water. And what do you understand by saying imprinted water? Imprinted by information? And if yes, imprinted, but which information and how you imprinted the water? Okay, because we can inform water on many ways. We can do it with crystal, with words, with exactly. Okay, so this part you want to keep for yourself. Okay, thank you.
Okay.
It seems to me that you should compare his water before imprinting and his water after imprinting. And you, yes, very same water. But now you compare different waters.
Not.
One vessel, and another is also from another.
We took one time control to control as a kind of baseline measurement, and then second time we took a control and experimental.
Experimental, I can give you just sole solution.
Yes, this is.
You'll see.
In this case, I mean, what we received there was a closed vessels. I mean, this 1 liter thing, and I assume they are, I mean, not chemically treated. No? It's basic assumption.
I'm sorry, probably I'm dull enough. What I don't understand. You see, you have your control. Your control is from the same vessel.
Yeah.
From the same
Yeah.
origin.
Yeah.
Yes?
Yeah.
It's the same water.
Same water.
Yeah.
Yeah? Now you take this water, or he takes your water, imprints it, and as you see, did it change due to imprint?
Yes.
Now you see difference between your water and his water.
No. It's he gave me control water. We asked. Yes, we asked. That was what we received.
Didn't say it.
Yeah.
So one portion of the same water.
Yes. And they use. Yeah. Of course. There's a meaning. Yes. Otherwise, I mean, everybody use different water, and we ask it more or less. It makes sense. I mean, to use the same control water that was used before imprinting, and then after. Of course, yes. There's a reason. Yeah.